The next guest speaker is online, and that's Professor Sebastian Verhelst from the University of Ghent. So I hope he's already in the room. I can see him on my screen here, and I hope we can hear you.
I hope so.
Yes, we can hear you very clear. All right, Sebastian. Yes, here you are. Welcome.
Good morning, everyone. And I hope that now you can see my screen as well.
Well, online we can see it already, but we are now switching the physical audience also to your screen. Yes, here we are.
All right, then I guess we're good to go.
Yes, welcome, and take the floor, Sebastian.
All right, so good morning, everyone. This is what we will be discussing today, how to green inland waterway transport. We've already heard Daisy mention a couple of options. There's a ton out there, it seems. Will we go for LNG, or will we have hydrogen to power this vessel? Will it be maybe ammonia or biofuel such as HVO? So there's a lot of questions out there, which I hope I'll touch upon, give you some insights on. Very quickly introducing myself, just to highlight some of the background that this is coming from. So my name is Sebastian Verhelst. I'm a professor at both Ghent University in Belgium and Lund University in Sweden. And I would just like to point out that I did my PhD on hydrogen engines, but we also worked on renewable fuels such as methanol, ethanol, straight vegetable oils, biodiesels, animal fats even. So basically anything that will burn in an engine and that has a renewable origin, we've looked into, just to hopefully give you the view on a fairly broad background that this will come from. And maybe also important to point out is that we've been increasingly focusing on marine applications since a couple of years. We led a work package within EU Horizon 2020 project called Lean Ships, where we converted a high-speed marine diesel engine to methanol operation. And I'm currently coordinating the Fast Water project, which, if you allow me just one slide of PR, is all about gaining experience with methanol as an alternative fuel in shipping, where we've already demonstrated a pilot boat that is currently operating off the east coast of Sweden. That's this orange boat here. And end of next month, we will be launching the Methatug, a methanol-powered tugboat, which will be operated by the Port of Antwerp, Bruges. So this will be using engines converted to methanol operation. Now, what do I have in store for you today? I don't want to throw a lot of data, a lot of studies at you. I would rather focus on a set of very basic tools and insights that I hope will serve you right to be used as base criteria. When there's yet another alternative popping up, how do you place that versus the others? With just a couple of base criteria, you can already get quite a long way. So I will be putting forward a structured approach for comparing options. I'll go into that in detail. I won't be focusing on engine technology, which is actually our main expertise. I'm an internal combustion engine guy, but these days you have to be very aware of what the fuels world is doing and what the energy world is doing. So this is how it all ties in. And rest assured, this is purely objectively, I hope, so there's no commercial interest here whatsoever. So let's get started, and let's get started from the basics. We've already heard it a couple of times today. Why are we here? We want to set out the path to sustainable shipping. That means, to me, that we really need to think long term. Although long term, as we've heard, is getting closer and closer, still it's important that we look ahead, think about where we need to end up, and that we think big picture. For shipping, for example, we will need an energy source. Now we know that as being a fuel, or renewable energy sources. We need an energy carrier, and we need an energy converter to power our vessels. So if we think long term, we need all of these three things to match a number of base criteria. One obviously is that all these things should be sustainable. So the energy source that we will be relying on in the distant future, or maybe not so distant, to power shipping, must be gotten from renewable energy sources such as solar and wind and bio, but also importantly, everything that goes into producing an energy carrier, a fuel, for example, an energy converter, be it a fuel cell or an electric drive or a combustion engine, all of the materials that go into making these things, we need to make sure that they are used in a closed cycle. That is not enough yet. Sustainable is a very important criterion, but equally important is scalable. We know about the tremendous challenge we have ahead of us. All of the materials that we're going to need to build these things, these fuels, these engines, these ships, we have to make sure that those materials are abundantly available, because that goes hand in hand with affordability. And as soon as you're talking transportation, obviously storability is very important. We need high energy density of the energy carrier, of the fuel. We need high power density of the energy converter, because we need to ensure range and payloads. So sustainability, scalability, storability sounds very simple, just these three criteria. That's what I call my triple S criteria to assess any option, but that gets you quite a long way. And I'll touch on some examples of that. So first one of this chain was energy source, and first criterion is sustainability. So let's check sustainable energy sources. Well, we know what those are. We know that we have biomass, we have hydropower, tidal energy, geothermal, wind, and solar. Now let's think of the second criterion. What's the scalability of these things? It's very important because we need to know in which of these things to really invest. If we look worldwide at the maximum potential of something like biomass, we get to the order of 7 terawatts of continuous power that we would be able to generate from that. That's a huge number, and a number that is meaningless to us unless I give you a benchmark figure. The benchmark figure is that we're currently at around almost 20 terawatts worldwide of power that we're using. So biomass can contribute to that, but it's quite some way short of what we actually need. Hydropower is a very similar number, also about 7 terawatt. And in this case, we're just looking at the theoretical potential. So we're not currently worrying about what that would mean for nature or for moving people or whatever, just the theoretical potential, because that gives us some pointers. Tidal, order of 14 terawatts, geothermal, order of 44 terawatts. So both look quite attractive, but both are also quite challenging to harvest. They're pretty harsh environments, quite dispersed environments, so not as easy to make use of. Wind is getting really interesting. That gives us 72 terawatts, so that definitely justifies all the large offshore projects, for example, we've seen come online in recent years. And then let's look at solar. Solar worldwide could give us something of the order of 85,000 terawatts, which obviously is no surprise given that all the other renewable energy sources I stated here, apart from tidal and geothermal, are basically just highly diluted forms of solar energy. So that is not saying that we should make use of biomass and tidal. We should definitely do that where it makes sense. But in the long run, if you think renewable energy sources, the base load will have to come from solar energy. And why am I telling you all of this? This seems very, very remote from inland waterway transport. Well, because future fuels will likely have to be made from the renewable energy source that is most scalable. So it seems that renewable electricity is going to be the most scalable renewable energy source. And thus, if you link fuels to that, we come to the topic of e-fuels, electrofuels. So that's still a vague category, a fuel made from green electricity. But which fuels should we then be looking at? And so first tool that you can use there is to realize or to think about the life cycle of a fuel or an energy carrier. Obviously, you have to produce it, so then it's very important that you check how efficiently you will be able to produce that fuel and how scalable you can do that. Once you have the fuel or the energy carrier, you need to transport it to where you want to make use of it. So from the production location to the point of use. A very important property there of the fuel or energy carrier is its energy density. And I'll give you some examples in a minute. And then finally, of course, what today is mostly about, which energy carrier do we want to use? There also energy density is very important, besides obviously how efficiently we can convert the fuel's energy to motive power and how clean we can do that. So just always keep this in mind with every new alternative that pops up, that we need to look at this entire life cycle of the renewable energy sources over producing the energy carrier. Here you see a couple of them already mentioned, so green hydrogen or synthetic methane or green methanol or green ammonia. We can have different forms. We need to make it into something that is storable, transport it, store it, so that we can then bunker ships, for example. So let's look at each of these pieces of the puzzle in turn. First piece of the puzzle: how will we produce those fuels, or what can the production insights tell us about which fuels to focus on? So first thing to keep in mind, of course, if in the long run we will need to be able to synthesize fuels, then at least let's make what we want. I'll come back to this, but energy density obviously is a very important one for transportation. But next to that, my view is also that we should preferably be looking at simple molecules. And there's a reason why you have this typical short list of hydrogen, methane, methanol, ammonia, because then obviously your production is more efficient. So if you think of the life cycle again of the energy carrier, this is about the well-to-tank part of the equation. Let's try to make that as efficient as possible. Second criterion: what about scalability? What can we actually make? Well, we have to look for things that we have abundantly available then. Things like carbon and hydrogen, oxygen and nitrogen, things that are abundantly available in the atmosphere or in the Earth's crusts, and start looking what type of fuels we can make with those. So then it's logical that you first end up with something like hydrogen, for example, or hydrogen derivatives, you could say, things like methane or ammonia or methanol or dimethyl ether. And obviously the list continues. You can definitely also make things like green diesel, as some people are doing, but you can also see that this list, that the molecules are becoming more complex. So you can also imagine that the more complex molecule, if you want to build it up from scratch, from the building blocks, that this is going to cost more energy. So it will become less and less efficient. And then how to actually compare this list that we have here. Well, one important distinction already, if you look at the different molecules here, is some have carbon in their structure, some don't. So a very important question here is, simply put, to carbon or not to carbon. This is a pretty complex graph that I won't lead you through. I just will point out some things. This is about converting renewable energy sources ultimately to fuels. And so we have things like ammonia here, we have hydrogen, we have methanol, we have methane here. And so for the things here that use carbon, obviously we will also need some carbon capture. And so how do these options compare? Building fuels from the building blocks using carbon or not? So what about the production efficiencies? There were a whole bunch of numbers in that slide. The interesting thing is, if you start comparing the production efficiencies of these things, the carbon capture does not come for free, but it's actually only a minor part of producing the fuels. It's actually the first step, producing the hydrogen, that is the biggest energy chunk. I've illustrated that here with a well-to-tank energy breakdown of synthesizing methanol. And you see that the big chunk really is electrolyzing water to produce hydrogen. That's about 70% of the energy that you need to produce methanol, as the example here. Obviously, you need energy to extract CO2 from the atmosphere, for example, and the other processes that you need to build the fuel. But surprisingly, it's mostly producing the hydrogen. So if you then think of ammonia, one of the other options that is being put forward there, actually Nitrogen, which is abundantly available in the air, you would imagine is easier to use as a hydrogen carrier, but splitting that very stable molecule of nitrogen is also very energy intensive. So the differences between producing methanol or methane or ammonia, there are differences, but they're much, much smaller than you would think. Probably a more important question to ask, whether or not to include carbon or not in the fuel, is obviously the future price of carbon, which was also just briefly touched on. So if we then compare the four options I've just briefly mentioned concerning production, if we look at something like hydrogen, which is fairly easily produced from renewable energy sources, or in a fairly straightforward matter, there you can say, well, this is really an essential building block. Green hydrogen is definitely going to be part of a future society relying on renewable energy. Question then is, of course, in which form. So we will definitely use it in the energy system. We will use it as a molecule, for example, for the chemical industry. Producing it compared to the other fuels I've mentioned is obviously the most efficient way, because that's the first step you take anyway, but it's not the only thing you should be looking at, which I'll come back to. Something like ammonia, obviously you don't need carbon, so that's a big point of attraction. It's also something that we have quite a lot of experience with. It's one of the top 5 chemicals worldwide, so as a chemical product, it's quite mature. Looking at production of something like methane, obviously now we need carbon, so we're making use of CO2 actually to bind the hydrogen into something that is maybe more easily handled, such as methane. That's, of course, something we know very well, because it's the main component of natural gas, and we have a vast infrastructure on that. But there's a big question mark, of course, on the competition that is going to develop going for sustainable carbon. So chemical industry needs carbon compounds. Aviation, we know, is a sector also vying for the most energy dense fuels. So there's an uncertainty on carbon price. There's a lot of development on carbon capture and utilization, on direct air capture, but there's a lot of experience still to be gotten there before we get more data, before we get more information on the actual price. In Europe, if we look at road transportation, carbon fuels are out, as you might know. So the legislative framework is there only focusing on tailpipe emissions. So keep in mind that a zero emission vehicle is a purely legal definition. Be very aware of what you're talking about when mentioning something like that. So if you draw your control box around the vehicle, then of course, if you have no tailpipe, you have no emissions. But if you look at the life cycle, it can be a completely different story. In the marine sector, luckily, there the focus now is on a well-to-wake greenhouse gas emission, so a carbon neutral fuel is definitely an option there. Now looking at methanol, obviously, again, you need carbon to produce methanol. It's also something that we're very familiar with, also in the top 5 chemicals, so a mature product. And also beyond its fuel use, it's through the methanol to olefins route quite attractive for converting our chemistry sector from the petrochemistry we have today to sustainable chemistry. Now I hear a lot of you thinking, okay, we have these fuels now that are being pitched a lot for maritime transports. I'm not too sure for inland waterway if this is the best option. What about biofuels? Short term, clearly something like biodiesel, rapeseed methyl ester, or hydrogenated vegetable oil. Those are the most interesting options. Why? Because they're drop-in solutions. We can use basically the same engine. We can basically use the same storage solution. However, again, this focus on long term, the expectation is that e-fuels will gradually take over. And the reason for that is twofold. One is, as I mentioned, the sustainability and the scalability of renewable energy sources. Already touched on that, but here, just as a visual representation, what type of green electricity you could get per year from 1 square kilometer of land. You can grow biomass on that land, or you can put wind turbines there, or you can put PV panels on there. Unfortunately, growing biomass is something that is a very low efficiency process. Photosynthesis just has very low efficiency. So if we look at square kilometers of land, we can just get much more energy in the form of green electricity than energy in the form of biomass. There's a biomass limit, which means there's an inherent cap on the scalability of biofuels. And that, of course, also goes hand in hand with the affordability. So the expectation is that initially the biofuels, because we know the product now, are cheaper actually than e-fuels, but in the long run, e-fuels will probably become cheaper than biofuels. So now we've looked at the production end of things. We need to produce energy carriers, fuels to power our transportation. Then we need to distribute, store, and bunker fuels. So the production, we don't know yet where that will happen. That will happen in various places worldwide, but we know that the places with the cheapest renewable energy sources are not really in Europe. So there's a very likely possibility that we will also import fuels. So we will have to think about the fuel infrastructure. And then we can use that to, again, think about, okay, are we going to look at hydrogen or ammonia or methane or methanol, for example? So are we going to look at hydrogen, or is a hydrogen vector going to be more attractive? So what's plotted here, if you just look at the blue bars, is the mass of hydrogen per cubic meter of compound. So if we liquefy hydrogen, so if we cool that down to minus 253 degrees Celsius, so 20 Kelvin, then we liquefy hydrogen, and then we end up with a certain mass per cubic meter, basically the density of our liquid hydrogen. And yes, you do see this correctly. So then we end up with 70 kilograms per cubic meter of hydrogen. So that's a very important one to keep in mind. It's illustrative of the huge energy density challenge of hydrogen. Basically, even liquefied, which is technically quite challenging, we end up with the density of styrofoam. So that's one thing. Second thing is, if you look at the other hydrogen carriers here, if you just look at the blue bars, it's clear they all outscore liquid hydrogen. So that's quite surprising that almost anything is better at storing hydrogen than hydrogen itself. So this explains why there's so much interest in these hydrogen carriers. And this is just the fuel itself. It doesn't stop there. So if you have liquid hydrogen, of course, you need something to contain it. You need a storage system. If you look at the heating value, first of all, so the energy density in megajoules per kilogram of fuel, we all know that hydrogen is really attractive, that it contains a lot of energy per kilogram. As you can see here, so we're talking 120 megajoules per kilogram compared to maybe 42, 43 for gasoline and diesel, so 3 times higher almost. So that seems very attractive. But then we mustn't forget that carrying hydrogen is really challenging. So for gases, whether it's methane or hydrogen under compressed form at 700 bar, so very high storage pressures, or liquefied form, we go from this 120 megajoule to ultimately a much lower value, because we have to count in the fuel storage system, the tank basically. For a hydrogen compressed tank, the tank weighs way more than the hydrogen it can actually contain. Similar thing for liquid hydrogen. So be very aware that as soon as you're looking at gaseous fuels, that you talk about the right thing, that you count the storage system in here. And that, of course, that means that for the fuel infrastructure, that the ease and the costs linked to that of distributing, storing, and bunkering fuels is very strongly linked with the energy density. So that's always one to really look into. I will touch on that again in the next section, because the use is also very heavily impacted by that. So let's dig into actually using these links. There's a lot of criteria actually that come into play here. I feel that There's a lot of studies there, mostly focusing on cost of production, and that's sort of don't touch yet on the differences in use of these different fuels. So that's really important. One is, of course, the conversion efficiency. Once you have produced the fuel, with which efficiency are you going to convert back to power? One is pollutant emissions, of course. What about air quality? But what about soot and NOx emissions, for example? The energy carrier that you've now produced, does it have a global warming potential? What does the onboard storage look like? What's the safety? What's the technology readiness level of the energy converter? Do we have engines? Do we have fuel cells that can operate on these things? So again, a couple of guidelines here. My view on that is, again, it's very interesting if we can keep things simple. If we produce simple fuel molecules, our experience has shown that converting these things back to power can typically be controlled more easily. You can end up with a better trade-off, for example, between the efficiency and the emissions, or even better, if you choose wisely, if you choose things like hydrogen or ammonia or methanol or things like dimethyl ether, you just completely eliminate soot formation. You can't form soot from these things. So then you don't have to worry about a trade-off between your engine efficiency and your soot emissions, for example. So this is the tank to wake part of the overall well to wake equation, which is, of course, also very important. And then if you think about using it and storing this on board, clearly something that is liquid at atmospheric conditions, that greatly simplifies the ship design. That makes sure that your range and your payload maximizes. So again, energy density, a lot of these things come down to that again. So let's look at some energy density and specific energy numbers for some energy carriers. Let's just look at the left plot here. This is showing on the y-axis the energy density in terms of how much energy do you have along with you if per liter of volume that you need on board your ship, for example. Versus on the x-axis, how much energy do you carry along per kilogram of the energy carrier that you're hauling along. We won't go into details here. Again, this is about providing insights. Very easily, you can see that clearly liquid fuels outscore others by an order of magnitude. And there's a reason why we're using liquid fuels today, of course. So whether you compress CNG to 250 bar or hydrogen to 700 bar, or you liquefy hydrogen, yes, you make it storable, but you still see this order of magnitude difference in energy density between something that is a gas at atmospheric conditions and something that is a liquid. And then we've heard batteries mentioned briefly. Well, the gases are still an order of magnitude better than batteries. So clearly here, that's the reason why there's another graph here just on a logarithmic scale to see some distinction between battery chemistries. Battery electric shipping is possible, but this will only be able to serve niche applications. So for the bulk, we really need the energy density of a fuel, and obviously volume and weight are important for shipping. The weight will affect the draught, will affect the resistance, and might prevent us from entering ports. The volume will directly compete with cargo, which is how we should earn the money. So with all these fuels, always keep in mind the storage system. Here there's a visual representation of that. If you have a liquid hydrogen storage system, okay, you need a tank to contain that. The tank needs to be round to minimize the heat losses. If you have a compressed system, that's the same thing. You know, the more sturdy vessel will be a cylindrical shaped or round shaped. So your effective volume on board your ship will be quite severely compromised if you opt for a gaseous fuel. If you go for something that is liquid at atmospheric conditions, such as methanol, basically the space you have available on board for fuel will almost entirely be able to be used for storing that fuel. So let's look at our four prime fuels again. How will we use them? For hydrogen, it's very compatible with the EU legislation that is tailpipe focused for road applications, but the big catch here is the very low energy density. That just makes handling the fuel, storing the fuel, very difficult, very inefficient. And so you're introducing inefficiencies all along the chain and introducing costs like that. Of course, once you have the hydrogen on board, you can convert that to power with high efficiency, with ultra low emissions. Even if you're using combustion engines, for example, then the only thing you have to consider is emissions of nitrogen oxides and emissions potentially of unburned hydrogen. NOx emissions can be controlled relatively easily. Why am I mentioning hydrogen explicitly here? Because hydrogen also has a global warming potential. And that's something that recently was made clear, that hydrogen does have a global warming potential. So it's 11 times as potent as CO2 as a greenhouse gas, and the effect is that of an indirect greenhouse gas. And of course, you can imagine that there was quite a bit of an outcry when this study became available. My personal feeling is that that's a bit exaggerated, because the hydrogen infrastructure that we're going to be building up, the expectation is that this is going to be much more leak tight than, for example, the natural gas infrastructure we have today, because it's always going to be quite expensive to produce the hydrogen. So we better make sure that nothing is leaking. Of course, if you look at schemes where people are thinking of retrofitting natural gas pipelines to then also pipe hydrogen, then of course the leakage is something that definitely has to be looked into. And if we're thinking of shipping liquid hydrogen, where we could end up with boil off, then definitely that's something to be very aware of. What about ammonia? There's a number of question marks concerning use of ammonia. There's a bit of an ammonia hype, as you're aware of, currently, mostly in the ocean-going world. That's an extremely toxic compound, toxic both to human and marine life. It's a gas at atmospheric conditions, although we can relatively easily liquefy it, but still, that has safety and cost implications to go with it. And if we have a nitrogen-based fuel such as ammonia, obviously nitrogen emissions are going to be a concern. One thing that we are not fully aware of, for example, is that we can also start forming N2O, laughing gas, which is an extremely potent greenhouse gas. Then we're talking about something that is almost 300 times as potent as CO2 as a greenhouse gas. And the worry is that we have no idea yet how to deal with them. We've seen test results now that where the N2O coming after the after treatment is actually higher than the N2O engine out. It's also quite difficult to burn. Basically, it doesn't really want to burn well. So basically, if you want to run on ammonia, you need to convert at least part of that ammonia back into hydrogen, which is a great fuel. So that's not looking very viable, I would say. Definitely not for inland waterway. If there's one application where we could use it in the long run, is the large two-stroke engines of the big container vessels that are currently running HFO that can basically burn anything, including ammonia. Also important is to realize that we're at a very low TRL stage, very low technology readiness level stage here. For methanol, that's looking quite attractive, looking at the entire chain, and also remember this use as a molecule. The unique selling proposition really here is that it's the simplest hydrogen carrier that is liquid at atmospheric conditions. And the fact that it's liquid makes the design of the vessel, storing the fuel on board the vessel, transporting and distributing the fuel much easier and therefore cheaper, of course. So for quite a number of applications, we will always need liquid fuels. So that also makes it easy to use. We also have a lot of evidence by now that we can do this with high efficiency and ultra low emissions. And also, interestingly, it's completely harmless to marine life. This is catching on. There's dozens of methanol fuel ships that are going to be sailing soon. What about methane? Again, quite attractive looking at the entire chain, because that's basically a mature industry. We have the LNG industry. There's a natural gas grid. We have existing appliances and vessels. But remember, it's still a gas, so we won't be able to use that for any vessel, because of the challenges in transport and storage. And there's also increasing concerns on methane release before and at the point of use, methane also being quite a potent greenhouse gas. Then finally, before we come to the wrap up, maybe some of you are also wondering what about combustion engines? Will we still have combustion engines, or are we going to be transferring to fuel cells? Well, the combustion engines remain attractive because they can run on all these e-fuels already mentioned, and they're sustainable and scalable technology. They're clearly scalable because there's 2 billion out there worldwide today. They're also sustainable because they're made of abundantly available materials, which are actually already being recycled today. So a very important message here is that we, yes, need to get rid of fossil fuels, but not necessarily of combustion engines. The combustion engines on methane, as you know, on LNG are commercially available. There's already engines out there commercially available for methanol. It's mostly work in progress with some engines now commercially available for hydrogen. And then for ammonia, it's still at the R&D stage. What about combustion engines versus fuel cells then? Interestingly, we're talking not about small engines, of course, for your applications. And combustion engines have higher efficiency the more highly loaded they are. Whereas fuel cells, there the efficiency drops with loads. And also the bigger a combustion engine is, the higher its efficiency is. So for the marine derivatives of truck engines, for example, we're talking about over 45% efficiency. The medium speeds and the 2-strokes, they attain over 50% peak efficiency. So that's actually perfectly competitive with fuel cell systems. So in my view, this remains the most likely mover for shipping also in the long run. On top of that, if we switch fuels, if we go to these e-fuels, we've also got experimental evidence now that we can get to higher efficiency than with the current fossil fuels. And then what about air quality? Well, zero impact emissions are perfectly possible. The effect on the efficiency then depends on the fuel. So whether or not you still have some emission formation mechanisms, or you can completely avoid them. And so whether or not you need after treatment. So a couple of takeaways. Clearly, hydrogen will be an indispensable building block. Our renewable energy system will need to rely on something that we can use to buffer energy, and sustainable chemistry will need this as a molecule. So we will actually always need to produce molecules, so to fuel heavy transportation such as inland waterway, but also as an input for chemistry. Which means that whether it's hydrogen or methanol or ammonia, we will definitely need to produce these things in the long run. Question then is, of course, which of these are we actually going to use as fuels? It's quite obvious, but I'll state it anyway. Any choice obviously is only as clean as its production method. So there's no inherent difference between molecules. Hydrogen or ammonia or methanol, if you look at today, they're basically all produced from natural gas, from fossil fuels. If we go to sustainable energy sources, we can produce all of these with net zero CO2 emissions, whether there's carbon in the fuel makeup or not. If we actually look at the chemical as well as the energy use of molecules, we will always need carbon and hydrogen and oxygen and some other things as well. So again, which fuels? Well, hydrogen's greatest challenge is its very poor energy density. So you immediately introduce a lot of losses if you want to directly use that as a fuel. So for a lot of applications, we really need a hydrogen carrier, a hydrogen factor. And yes, that can include carbon. And there's a good reason for actually including carbon, because we get increased energy density. And that comes with a greatly increased ease of use. And that easily outscores the increased energy expenditure that you need to produce a carbon-containing fuel. And obviously we'll always need carbon. So luckily legislation had at least seen this for waterborne transports, that we need to look at this from a life cycle basis, so that it's not just about the tailpipe. And then my view on things are mostly to keep things quite simple. So if we produce fuels, keep it as simple as possible. Yes, we could produce a green diesel, but why would we? Why not keep it as simple? Because then we increase the production efficiency. And on top of that, we also increase the use efficiency. If we think about simplifying storage, clearly opting for liquid fuel expands the number of applications that you can actually handle with that. So and that means that something like methanol is much more viable as a fuel than ammonia. So where will we end up in the future with these things? I hope I haven't raised a ton more questions than you started out with. I hope I've given you a couple of tools to try to make the link between all these fuels we see popping up and what this could actually sail on in the near future. So thank you very much for listening.
Yes. Thank you very much, Sebastian. I think the final words are quite true. The links were made, at least for me, they were made. It was a very, very, very interesting presentation, at least from my side. I hope the audience agrees. I saw there was a question in the chat already. It was raised at the beginning. Maybe I'll read it up front. It was a question on the terawatts. You said that the global demand was 20 terawatt and that the yes, right? Is someone speaking in the audience?
All right.
No?
Yeah, I've picked up the question in the chat here. So the question is that the 20 terawatts, what did that number refer to? It's global, worldwide power consumption, everything included. So it's not just shipping. It's our global needs. Yeah. And so what I was trying to get across is where are we going to get that from? And the good thing is there's an abundance of renewable energy. There's more than enough solar energy, but of course the challenge is to actually start harvesting that. Yeah. And it's a power figure, so it's a continuous figure.
Yeah. Very clear, very clear. Okay. We have another question in the chat. We see that methanol looks as one of the most attractive fuel for storage and use in inland vessels. But what are the main challenges for production with methanol? And are there any forecasts on possible production as an e-fuel?
Yeah, that's a very good point indeed. There's technology out there now to sail vessels on green methanol. We're also demonstrating that in the fast water project. But indeed, the bottleneck now is the availability of green methanol. Yeah. There, an enormous breakthrough, I think, happened very recently when Maersk, the big container company, ordered methanol vessels and ordered methanol factories along with it. So they have a roadmap to go to sailing on green methanol, but they also realized, well, we need quite serious quantities of green methanol then. So they ordered factories to produce green methanol with that. As an example, the pilot boats I was mentioning in the fast water project that is currently sailing on biomethanol that is coming from the forest industry in Sweden. In the paper industry, you have the side product called black liquor, and that can quite easily be converted to methanol. So on a life cycle basis, that's very attractive in terms of carbon reduction. There's lots of plans for going from wind to methanol. You may have heard of liquid wind. They're developing such these green methanol factories together with Maersk. They're factories, for example, in the port of Amsterdam by Enerchem that are going to convert waste to methanol. So a lot of things are happening, but I think the important message here is that currently it seems like the demand is still quite a bit bigger than the plans for production. So that's a major challenge.
Yeah, chicken and the egg story, I think.
Yeah, indeed.
Yeah. Well, a final question. We see here why you excluded liquefied biomethane as a zero-emission fuel.
Yeah, I didn't exclude it. I talked about methane, so that's basically the same thing. So you can use go to compressed storage, you can go to liquid storage, but the points I put forward still apply. It's a gaseous fuel, and the points that I raised with methane perfectly comply to liquefied biomethane as well.
Yeah, all right. Then I'm looking at the physical audience. There's some questions here. Yeah.
Thank you very much for your interesting presentation, Karl Verhamme, de Vlaamse Waterweg. I have a specific technical question relating to ammonia. Isn't it, to your opinion, more corrosive for engine parts, and then perhaps to a lesser extent for inland waterway vessels, but perhaps for marine vessels. So what's your idea about that?
Honestly, my current take is that this is a minor concern. I think we will deal with corrosivity issues. I think ammonia has much bigger challenges to overcome. I think if we, again, think of the main application where I see potentially a use of ammonia in the long run, it's the big two strokes for ocean-going vessels. They're running on heavy fuel oils, which is sort of the waste products from refineries, as you know. So that's already a really dirty fuel that they know how to handle, that they have developed lube oils for. So I'm pretty confident that they would be able to meet these challenges, also concerning corrosivity of ammonia. But I think there's bigger fish to fry there.
Yeah. Okay, clear. Ja, zeg maar.
Foto's, oud, water en oud. Maar op een gegeven moment, water gaat stilletjes verdwijnen. Leven meer. Al dat. Centrales gaan in draaien. Water meer. En ook uitdroging van het gedrag en extreme stormen niet meer wegens en de zee, al wat dat aangedreven en al.
Ja.
Maar door de extreme stormen dat we krijgen, zonnepanelen.
Okay, I understand the question. So the question, Sebastian, is we have a lot of alternative energy sources you mentioned in the very beginning of your presentation. Do the climate change, does it impact the sources, in your opinion? Does it impact the fact that it will be more severe and more extreme and therefore maybe unreliable, the alternative energy sources?
I'm trying to... I think there's a link actually with the necessity of e-fuels. I only very briefly touched on that topic, but if we want to transition from a fossil-based society to a society running on renewable energy sources, and yes, indeed, global warming is already making winds more extreme, for example. That to me will only increase the necessity of being able to store, to buffer energy at very large scale. There's different numbers out there, but one I've seen is that as soon as we rely for over 80% of our energy input on renewable energy sources, while these are very intermittent, so we need to find some way to buffer energy on massive scale. And the only way that is feasible or economically feasible is to use the energy density of a fuel. So also there, the energy density of an energy carrier comes weighing in.
Yeah, very clear. So storage is quite important there. Okay, thank you, Sebastian. I don't see any other hands raised, so I'm going to conclude here. Do you have a question? Yeah.
Good morning. Are there also studies about the difference between the energy we put in an engine and the energy we take out? Because there is a big difference between a diesel engine. I think in the inland shipping we take about 5% out. The different we put the energy in.
Yeah, very, very good point. It's what I feel is missing in a lot of studies, as I was saying earlier, which stop at, okay, this is the most interesting fuel to produce. I think that explains a lot of the ammonia interest now, because on the face of it, it's slightly cheaper than producing, for example, methanol. But if you then look at actually using the fuel, it will be much easier to have a very efficient conversion of methanol to motive power of the ship than of ammonia, of something that is a bad fuel to begin with. So it's these two pieces of the puzzle: producing the fuel, how efficient can we do that, and then using the fuel, how efficient can we do that, which are equally important.
Yeah, and I think every source of energy has their efficiency numbers, right? It's part of how we use the fuel, indeed. All right, that's quite clear for me. So we have to include and keep in our minds that e-fuels are quite necessary in the future, and a transition could be a biofuel. That could be a quite important transition fuel as well. We have a net zero approach. We don't only focus on tailpipe emission, on zero tailpipe emissions. I think that's quite necessary for inland navigation as well, because if we do that, then the net zero approach disappears. We keep it simple, and it's not only about the use, it's also about the production and about the storage of the fuels in order to decide which one we take into account. Okay, Sebastian, thank you very much, all the way from Sweden, especially taking online time for us. One big applause, and then we continue to the next one.
My pleasure.